In this video, we are going to go over how to create a MONPNT3 entry for MSC Natsran. So the MONPNT3 entry is one of many monitor points available in MSC Natsran. So this is what you can expect towards the end of this video. Here are some examples of the entries I'm going to create. So here, by the end of the video, we are going to create two MONPNT3 entries. So first, I'm going to walk you through how to create one or two of these entries. I'm going to go over how to interpret some of these results. I'm going to output the results to a CSV file. I'm going to orient the monitor points, and then I'm going to talk about possibly a faster way to create these entries. We're going to use a CSV file. Okay, so let's go ahead and get started. Now, there are some definitions I want to clarify here. Some of these definitions are not clear in the documentation, so that's why I want to take time right now and go over these. Okay, so let's look at the loads and boundary conditions for this Natsran model. So I have two beams. These beams are fixed on one end and then loaded on the other end. So let me go ahead and show you what the configuration looks like. So again, one end is fixed, and then on the free end we apply a load. Here this beam has a load of about 10,000 newtons. This other beam, although I used a series of force entries, the total load is 10,000 newtons. Okay, now these are some of the definitions we should be familiar with. So if we have our beam here, and then one side of the beam is fixed, and then one edge of the beam is loaded. In the documentation for, let me go ahead and find it. Oh, one last thing. All of this information is coming from the following documents: a quick reference guide, the linear static analysis user's guide, and the aeroelastic analysis user's guide. Each of these documents has more information on monitor points and MONPNT3. So let's go ahead and jump to MONPNT3. Now, when you read the documentation on MONPNT3, they use a term that's called upstream and downstream. So here are loads that come from the elements upstream of the cut. They don't clarify what downstream and upstream are. So here, let me take an attempt to describe what upstream and downstream are. So here we know one side is fixed and then the other side is loaded. So we know the load path is something like this. The load is going to travel from the loading area to the supported area. So this is what the load path might look like. This is one interpretation. Don't take this literally. It's just a general idea of what the load path might look like. Now, you can think of this as being a river, right? So then we have terms for upstream and downstream. This region here could be considered upstream, and then this region here could be considered downstream. So just keep that in mind. When I'm using upstream and downstream, this is what I'm referring to. Upstream means the load is coming from somewhere, and then downstream, the load is going to somewhere. Okay, now this is why we want to define a MONPNT3 entry. Let's suppose that I want to make a cut in this beam, and I want to determine the equivalent loads along that cut. So let's suppose we make a cut here. So then we have a new beam here. Let's draw a free body diagram. So we have some reaction, some moment, and then we'll have the same on the opposing side. We'll have some moment, some reaction. These are unknown to us at the moment. This is what we want to determine. This can be determined with a MONPNT3 entry. So what I'm going to do is this. I'm going to define these elements. So we think this is meshed. Let's suppose this is the mesh here. And then here, 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 and here. We are going to define a MONPNT3 entry that does this. First, we want to identify those nodes on the cut. So these are the dots that are along the cut, the nodes that are along the cut. And then we want to select elements upstream from the cut. So these elements here that I'm shading, these are the elements upstream from the cut. So these elements, the force provided by these elements is going to be fed in to these, or actually for these nodes, these black nodes, these elements are going to contribute forces to these nodes. And then those forces on these nodes, it's going to get resolved into one point, the monitor point. And this is going to give us the loads at that cut, if you will. So that's the motivation. We want to get the loads at this cut, at this region that you see here. So how do we do this? So let's go back to the pre-web app. In this window, there are no monitor points. I'm starting from scratch. We are going to take the cut. Let's see, where am I going to make the cut? We'll do it at 3 meters. So here, this is 0 meters, 1 meter, 2 meters, and then 3 meters. So this is where we want to make the cut. We'll do the cut for the beam elements and the 2D elements, just so you see what the process is like for both of these. Okay, so let's go ahead and get started. So to do this, we first need to create a set 1 entry. So let's go ahead and look for set 1. So that would be this entry here. We are going to create 4 sets. So we'll call this 101, 111, 201, and then 211. Now for 101 and 201, those are going to contain the nodes on the cut. So let's go ahead and pick some nodes along the cut. So we'll pick a node along the beam. So we want to cut at 3 meters. So 0, 1, 2, and 3 meters. So we want to cut here. So we'll select this node. And then we'll repeat that for set 201. And here I think I have to angle this a little better. So let's look at this from the side. Let's rotate this a little. Okay, so these are the nodes I want to select. So let's go ahead and select these nodes. So let's make the picking sphere a little smaller. It's going to be really small, but it's there. Let me increase the size a little. Okay, so here's the picking sphere. Oh, is this right? Right, so it would be these nodes. It's very important you pick the right nodes, or your answers are going to be a little off in the demonstration. Okay, so we'll pick these nodes along this cut. And now rotate the model. Make sure you've selected all the nodes along that cut. You can see that this node here was not selected, so we'll make sure we select that. Okay, let's rotate this. Okay, so all those nodes have been selected. Now, the next thing to do, we need to pick elements upstream from that cut. So for the beam elements, we're going to pick an element here. So this node here is where we cut, and then this element is upstream from the cut. And here on the far right, that's where we apply the load. Remember, upstream is where the load is. The load flows from upstream, downstream to the support, so from right to left. Okay, now for this last set 1 entry, we're going to pick elements to the right of the cut. So again, these elements are upstream from the cut. Okay, now we have to create AE comp entries. If we look at the MONPNT3 entries, you need a few things, or actually maybe I could just, we do not need an AE comp. We can just select the set 1 entries we defined a moment ago. So here, what I did was the following. I created set 1 entries that define the nodes and the elements along the cut. And now I can create a MONPNT3 entry. So MONPNT3, let's go ahead and open that. Let's create 2 monitor points. So we'll call this monitor point 1, monitor point 2. And we'll say this is the cut on beam 1 at 3 meters. Okay, so I'm going to call this beam 1 and then beam 2. So just so you're aware of what the beam 1 and 2 are. Okay, then I'll hold off on the axes for now. Okay, let's go and do this. Let's go ahead and save for grid set. Consider set 101, which has the nodes at the cut of beam 1, and set 201, which has the nodes on cut beam 2. And then select the set 111, which has the element IDs for the cut on the beam elements. And then set 211, which has the 2D elements on the cut for the second beam. Okay, then here, what you want to do, you want to track the forces along the X, Y, and the Z, and the rotations about the X, Y, and Z. So components 1 through 3 and 4 through 6. And we'll do that for the second one. Okay, let's look here. Right, so now we have to position our monitor points. So the first position is going to be at this node here. So this node, I already know this because I've done this exercise before. This node is going to be located at 3, 0, 0, or X, Y, and Z. So we'll go ahead and do this. We'll type in 3, 0, 0. You could leave them blank and the default is 0. Let's go ahead and now turn on that first monitor point. So MONPNT3, that's the first monitor point at this cut. Here I turn on this checkbox, and here in the detail, this shows me additional information about that monitor point. The large square, that's the location of that monitor point. This sphere represents the element that's going to be contributing to this monitor point. And then if I want to, I could turn on a label, and then I see the name of that monitor point and the label for that monitor point. Let's go ahead and do the same thing for the other monitor point. You'll notice one thing about the second monitor point. The default position is at the origin, so that's why it's located here. We need to position that monitor point at this location, which is about here. So that would be at the shear center of this other beam. So we want to locate it, situate that monitor point here. How do we do that? Again, I already know where that location is. I believe it was -2. And then when we do that, all right, so here you can see the updated location for that monitor point. And then let's go ahead and turn on the labels for both of these. Right, so if I look at this from the side, both of those monitor points are at the same location on the XY plane at least. But if I move these a little, right, so let me say that again. So both monitor points are at the same location on the XY plane. If I move this a little, you can see that they're both at the respective section in both beams. Okay, now let me turn on these checkboxes, display detail. So for this monitor point, this is what we can determine based on what we see on the screen. Let me go ahead and do this. Let me turn this off. So the large square represents the monitor point. The smaller squares represent the nodes that are going to contribute loads to that monitor point. The spheres indicate the upstream elements that are going to contribute loads to these nodes. So now if I turn that on, this is what that looks like. Okay, now we're done with these monitor points. Let's go ahead and now run Natsran. And one thing about monitor points, you need to turn on the output of that. You do this with the following command, monitor. Here we turn on the checkbox for monitor. Make sure to do this for the above subcase level. So here we have monitor, mark the checkbox for above subcase. You'll notice it's now available here on the right side. And here I set it to all, so I'll put all the monitor points. Okay, now when we run this, we will get the monitor points available in two places. We will get the monitor points in the F06 file. So let's scroll here and scroll down and see if we get monitor points. Okay, so we get monitor points here. You could get this data in a different way. You could either download the F06 file, or you can copy this data to a different text file. So it's really up to you how you want to look at this file. So again, you can just copy and paste that data for the monitor points, or you could download the F06 file and look at the same data. So here's that same data. Okay, now let's look at this. So remember that we have on the right side, we have for both beams, we have a load of about 10,000 newtons. And then here, if we go out 1 meter and 2 meters, this is where the cut happens. So what do we expect? We expect a shear force of about 10,000 newtons here, and we expect a moment of about 20,000 newton meters here. So if we look at the monitor points, that's exactly what we get. Along the y-axis of the monitor point, so that would be this green axis. So this green axis is the y-axis, this blue axis is a z-axis. So along the y-axis, we get negative 10,000 newtons for both monitor points. So we have one monitor point on this beam, and then another monitor point for this other beam. So let me turn on the markers here. So that's what we see here. And then what about the moment? So we want the moment about the z-axis of the monitor point, which is negative 20,000 newton meters. Okay, so this makes sense with a quick hand calculation that we did. Okay, now how do we look at the results? You can go into the Post web app and select the MONPNT3 dataset. Mark the checkbox for subcase 1, subcase 2. If you add 100 subcases, you could select the checkbox for subcase 100. Here in this other, and let me move this to the right a little. Now let me turn on these labels actually. Okay, so here in this box, if you will, you could turn on the different components of that monitor point. So let's turn on the CY component and make sure that the force is negative 10,000 newtons. So we'll mark that. We'll click on arrow plot. With the arrow plot option, it will actually show you arrows. So it gives you a general idea of how the force and the moments are situated. So here we see the force is negative 10,000 newtons, and then here also at the cut, the shear force is negative 10,000 newtons. What about the moment? So here you can press and hold the control key, and that will let you select different components and plot them at the same time. So here we see that the moment here is negative 20,000 newton meters, and then here at the other monitor point, it's the same value, negative 20,000 newton meters. Okay, now there is another way to do this, so I'll show you how to do that right now. If you have an existing H5 file, like I did here, everything that you run here with Natsran, you could click the download links and download that to your desktop. Also, another thing, if you've been watching all these videos, I'm doing all of this in a web browser. You might think that it's only available from this website. It's not. If you want to download your own installer and install your own web app in your own company, office, and so on, we have an installer you can download and do that. So here, let's suppose you have the H5 file on your desktop. You can open another tool called the HDF5 Explorer. So all of this data, we want to do this now. We need to output this data to an Excel or CSV file. That's what I'm going to do now. I'm going to take that H5 file, this H5 file. I'm going to upload it here. I know many of you might be tempted to read this data from the F06 file. I always encourage my developers and any other young developers, hey, save yourself the trouble. Avoid reading the F06 file as much as possible. Yes, it will work, but does it make sense to spend 1 week or 2 weeks trying to write your own script to do this? This is what I recommend. Read the H5 file. You can use Python to read the H5 file. In fact, I make some scripts available for free that will let you read the H5 file with Python. Alternatively, you could upload the same H5 file here to the Explorer. you can select the MONPNT3 dataset. The same quantities that we had in the F06 file, they're available here. If you look at this table here, let me look at what's going on here. The first two rows are the MONPNT3 entries we've created. You could do a few things here. You can create a plot. So here, I don't know if this will work, but we'll see if it does work. Right, so here are the monitor points. So here, the first monitor point for beam 1, here on the left bar, the center bar, this is the monitor point for the second beam. This third monitor point, this is because I used the MONSUM1 entry, so I'll cover that in a different video. You can see the shear forces are the same, and here let's look at the moments. So negative 20,000 for both monitor points. You can make bar charts here, or you could download a CSV file. So you'll notice now on my desktop, I have a new CSV file called acquired dataset. So you notice that I didn't have to labor away trying to read the F06 file, which is possible, but it's just very difficult, very time consuming. We're engineers, we are not coders. Here we let the web app get that data for us and extract the data and download the data to a CSV file. You notice here in the CY column, that's the same data for the shear force. And let's go ahead and do this. Let's go ahead and maybe create plots for the moment and the shear forces. So let's go ahead and create some bar charts, and let's go ahead and do that for the first two monitor points. So here you have it. So in blue, we have the shear forces, and then in orange, we have the moments at that cut. So here in red was the monitor point. We selected the upstream elements, and then after doing all of this, we got the equivalent loads at that cut. Okay, now a few additional comments. Let me look here. We went over how to create one monitor point. We went over how to create or interpret the results. We went over how to look at the results in the post web app, how to export the results to a CSV file. Okay, I'll get to this in a moment. Now, there's one option that I have to mention. That's going to be the X flag option. So if in the event there is a load where you have the monitor point, MONPNT3, let me show you that one. So suppose there was a load here. Some of you may want to include the load in the calculation. Others might want to exclude the load from the calculation. So the way you would include or exclude it is with the following option. You come here and you look at the X flag option. So here what we're going to say is, for this monitor point, if there was a load, we would say, you know what? A lot of the time you see this. You see the SMAD option selected. This just means, okay, determine the total load or the equivalent loads, but do not consider the loads from SPC forces, MPC forces, or applied loads. So here again, we're excluding loads from any applied loads. So I figured I'd throw that in there. Again, if your monitor point is considering nodes with applied loads, if you want to consider the applied loads, you set that to blank. If you want to exclude those additional applied loads, you would select these options. Actually, you just need one option, but in a lot of the examples I've seen, they just select SMAD, or it was in SMAD rather, SMAD. Okay, one other thing, orientation. So when we look at the monitor point orientation, this is what that looks like. And a lot of the time, I like to use a stick figure to represent the observer at the monitor point. So the loads at the cut are being observed by this coordinate system, if you will. Now, suppose you wanted to orient the coordinate system a little differently. Or suppose you want to change the position of this coordinate system. Let me change the position. So instead of here, let's move it over to -3 as an example. So now the monitor point we're going to be observing the loads at the cut at this location. Now, suppose you want to change the orientation. You can do this with a different coordinate system. Here you can see I have a coordinate system that's oriented a lot different. So this is what I'll do. I will modify the CAD field. I will select this coordinate system. And then here we'll see the monitor point has a different orientation rather. So the observer is now different. The same loads are going to be observed from a different orientation. So when we run this, let me see if I have this available. I believe, okay, right. So let's do this. Let's go ahead and rerun this. So I've only modified the second monitor point. The first monitor point is untouched. So if we look at the F06 file, let me download that new F06 file. Let me move this to the side. So here on the left were the original forces and moments for the original monitor points. Here on the right are the new values after I changed the position and the orientation of the monitor point. So if we look at the second monitor point, you can see that the shear force on the Y and the Z direction, they're different now. Actually, all the values are different. The reason the values are different are for the following reasons. The position of the monitor point is different now, and the orientation of the monitor point is different. This observer is different than before. So this observer is going to see the forces and the moments in a different orientation than before. Okay, so that was the X flag and the CD field. Okay, how do you create hundreds or thousands of these monitor points? So if you want to create hundreds or thousands of these monitor points, you go through the process of creating multiple set one entries. You could do this one by one. Let me see if I'm in the right window. It was this window, sorry. You would create multiple set one entries. So remember, set one entries, one set of set one entries defines nodes at the cut, and then the other elements define the elements at the cut. So here, remember, the squares, the small squares are the nodes at the cut, and then the circles are the elements at the cut that are upstream from the cut. Okay, let me look here. Let me look. Right, so you can either do this manually one by one, or you can download a CSV file and use the CSV file to, let me see. Right, so here's that CSV file. You can use Excel to help move with the procedure a little faster. Here, we did this for set one. Let's go ahead and do this for maybe MONPNT3. Download a new CSV file, and then I'll open this in Excel. And then here, let me just create a bunch of other monitor points, just so you see that the procedure is the same as before. So we'll use 201 maybe, and then 211. So 201, this column again, the grid ID is at the cut. And then here, element set, those are the element IDs at the cut that will contribute to the monitor point. And then the X, Y, and Z location. Here, I'm trying to use 211 here. Finally. Okay, so here, I'll just type in random values here, 1, 2, and 3. And then 1, 2, and 3. And then we'll save that. And then we'll go back here and then we'll upload these new monitor points. So here are all the new monitor points. You could do a few things here. Let's go and display more rows here. If you want to build the monitor points in the web app, what you can do here in the output window, you can copy this to a new text file. And you can now import these to Patran or MSC Apex or some other pre-processing tool for Natsran. The other thing, you can confirm the monitor points like you'll see here. So here you can see we have a lot more monitor points because we've created a lot of these. And since all of these are using the same nodes and elements at the cut, they're all of these monitor points are sourcing data from the same nodes and elements. So that's why you see a lot of dashed lines go to the same cut region. Again, the reason is because we're using the same 201 and 211 set 1 ID numbers. They're all using the same nodes and element IDs on the cut. And then here, if you wanted to, you could open or you could display the labels. And here you see that I didn't populate the labels column, but you could do that here, or you could even do that here in the web app. So I'll show you how to do that. Suppose, I don't know, if for some reason you wanted all of these to have the same label. You can type it in this row and click apply, and now every row has the same value. And then you can do that for every other column in this table. And then the process is the same as before. Let's see if this will run actually. So we're running this with all the additional monitor points. I expect this to work, but you never know. There could always be an issue. Okay, so it seems like it ran successfully. Here, we'll open the HDF5 Explorer, and I quickly need those values for the monitor points. So here, I'll quickly go here. I have values for all the monitor points I created. Click on download CSV, and now I have a copy of this on my desktop. So here are all the forces and moments for those monitor points I created with Excel. The alternative is a slower process of reading the F06 files. So you now have to read all these individual monitor points, and now you have to deal with all the different subcases, all the names, all the blocks, and you can see doing this by hand, it's very tedious. But here, we're not about that. We just use the HDF5 Explorer. We get our data, we're done, we're moving on to the next process. Okay, let's go and look here. Right, so that's how you build these MONPNT3 entries. They're very useful for getting the equivalent loads at cuts. And then the last thing for today's video, just in case you have questions or comments, I'll leave my email address here. If you have feedback, questions, comments, if you want access to the web apps you saw today, feel free to reach out and I'll get back to you as soon as possible. And as always, thank you for watching.